Good evening, students. So we'll see today's class we'll see about Gauss law. So earlier classes I've started the introduction about Gauss law and its applications. So we'll recap again what is Gauss law and we'll just carry on with our Gauss law applications. So what is Gauss law? So Gauss law states that the total electric flux psi through any closed surface is equal to the total charge enclosed by the surface. Okay. So we know that electric flux is represented by the symbol psi. So this is the symbol psi. Hope you can see the cursor. And the charge is represented by Q. So Gauss law states that the total electric flux psi through any closed surface is equal to the total charge enclosed by the surface. So electric flux is given by psi and any closed surface is equal to the total charge enclosed. So total charge enclosed, I have represented charge, I have represented with the symbol capital Q. It is total charge enclosed, so I have put a suffix enclosed, ENC. ENC stands for enclosed. So psi is equal to, that is the total electric flux is equal to total charge enclosed to that by that surface. So psi can also be written as, in the place of charge Q, I can write it is a closed enclosed surface D dot ds. I can also write the enclosed charge with respect to volume also. So integral V rho V dV. So converting a surface charge to the volume charge is called as Gauss law. So charge can also be represented as closed surface integral d dot ds, which is also equivalent to the volume integral rho v dot dv. Okay, it is also equal to the volume integral rho v dot dv. So applying divergence theorem, the surface integral can be converted into the volume integral. So applying divergence theorem for the right hand side, that is rho v dv. For that term, if you apply the divergence theorem, rho v dv, when applying a divergence theorem, it can be written as del dot d dv. So converting the surface integral to volume integral. So closed integral, yes, d dot ds will be equal to integral with respect to volume del dot d into dv. Therefore, from this equation, we can conclude d is nothing but del dot d. Okay, capital D, rho v is nothing but del dot d. So this is the Gauss law. This we have seen in the last class, and this is also called as the first Maxwell's equation. So what are the applications of Gauss law? So Gauss law provides an easy means of finding your electric field intensity, which is represented by capital E, or it is easy way of finding the electric flux density, which is represented by capital D, for symmetrical charge distribution such as point charge, infinite line charge, spherical distribution of a charge. So under applications of Gauss law, we are going to define the Gauss law for a point charge, for an infinite line charge, and for the spherical distribution of a charge. So if there is symmetric charge distribution, we can construct a mathematical closed surface which is called as the Gaussian surface. So capital D is nothing but the electric flux density. So capital D should be normal or tangential to the Gaussian surface. That is the property, or that is the condition to be followed. So for normal, d dot ds will be equal to dds, where cos 0 is equal to 1. Whereas for tangential is nothing but cos 90. Cos 90 is nothing but 0. So d dot ds is equal to 0. So for normal, d dot ds will be equal to ds. For tangential, d dot ds will be equal to 0. Okay. So Gaussian surface is chosen so that your electric flux density is constant in the parts of the surface for which d is normal to the surface. Therefore, we can bring d outside the integration sign, because d is treated as constant means we can bring outside the integration signs. So we know that psi is equal to, that is electric flux is equal to total enclosed charge. So that we have represented as capital Q suffix enclosed. Therefore, psi is equal to enclosed surface integral d dot ds. So when we are applying this on the Gaussian surface, your enclosed charge will become q. So for point charge, q enclosed inside the Gaussian surface, whereas when we write for line charge, then volume charge, and the for surface charge, enclosed charge will be equal to integral rho L dl, where rho L dl represents your line charge density. So total charge enclosed inside Gaussian surface for line charge distribution with density rho L coulomb per meter. Whereas for surface charge distribution, your enclosed charge can be represented as integral rho s into ds, and its unit is coulomb per meter square. For volume charge, it can be represented as integral rho v into dv. So for volume charge distribution with density rho v, the unit is coulomb per meter square. So now we'll see the applications of Gauss law. So first application of Gauss law is infinite sheet of charge. So we are taking here in this, we are taking a sheet of charge in the xy plane. You can see x, this is a sheet of charge. Okay. So follow my cursor. This is the sheet of charge. So this sheet of charge I am choosing in the xy plane. Therefore, it is nowhere related with z axis. In the xy plane, I'm assuming a sheet of charge. Therefore, z is equal to 0. As I said, since it is placed in the xy plane, there is no relationship for the sheet of charge with respect to the z axis. Okay. So, and once I assume the sheet of charge in the xy plane, I've taken a rectangular box. So in the rectangular box, I'm cutting the rectangular box in the center so that the sheet of charge crosses the rectangular box. So I imagine this is a rectangular box and the sheet of charge is passing through this rectangular box. So this is the rectangular, this is the sheet of charge which is passing through the rectangular box. So towards this side, an, small a represents your unit vector. An represents your normalized unit vector. So along this positive z axis, we call it as plus an. Along the negative z axis, we call it as minus an. Okay, so this side is positive normalized unit vector in the positive z axis, and this is normalized unit vector in the negative z axis, and your electric flux density will be towards this side. So keep it in mind that the electric flux density and electric field intensity are perpendicular to each other. So this sheet of charge is having a surface charge density rho s, and this sheet which cuts the rectangular box, its surface area is represented as ds. So this rectangular box is called as the Gaussian surface. So whatever we have seen in the diagram, the same thing we will see. So consider an infinite sheet of charge, uniform density rho s. So this is your infinite sheet of charge. So this is your infinite sheet of charge. Please follow my cursor. So this is your infinite sheet of charge which is having a charge density rho s, and this sheet of charge is placed in the xy plane. Therefore, it is understood that z is equal to 0. So consider a rectangular box as a Gaussian surface which is cut by the sheet of charge to give the surface area of the surface area ds is equal to dx into dy. So as I said you earlier, I have assumed a rectangular box. So my imagination, what you have to imagine is this sheet of charge is passing through the rectangular box. So which passes through the rectangular box. So this is the sheet of charge. So this sheet of charge surface area is represented by ds. Differential surface area is represented by ds. So dx is your sheet of charge, this sheet of charge, and the portion which cuts the rectangular box also lies in the xy plane. Therefore, your differential surface area will be equal to dx into dy. We know that z is equal to 0. So therefore, your differential surface area will be equal to dx into dy. Now, we know that D, capital D represents your electric flux density. As I said you earlier, your electric flux density and electric field intensity, capital E, are perpendicular to each other. So, capital D, that is electric flux density, acts normal to the plane. So, along the positive z axis, we call it as the positive normalized unit vector, and along the negative z axis, we call it as the negative normalized unit vector. So rather than specifying in the z direction, I'm just specifying in terms of the normalized unit vector. So along the positive axis, I represent by plus CAN unit vector. Along the negative z axis, I'll represent it as minus AN unit vector. Therefore, D will be equal to 0 in the xy direction. That is, electric flux density will be equal to 0 in the xy direction. So hence the charge enclosed can be written as, we know that earlier only we have seen for Gauss law, Q is equal to closed integral closed surface integral d dot ds. We can also write the charge in terms of volume integral. So just before 5 minutes we have seen, so surface integral d dot ds will be equal to the volume integral of rho v into dv. So here we have taken surface integral d dot ds because we are going to find the Gauss law for an infinite sheet of charge. So usually for an infinite sheet of charge, we used to find the surface integral. Therefore, Q is equal to, so if I take this diagram again, so you have to find the sides. So for this diagram, you have to find the sides, you have to find what is the top and what is the bottom. So what is the surface area along the sides? Okay, surface area along the sides, and then we have to find what is the surface area in the top side and in the bottom side. So I can write here, so my charge Q can be written as, this is a generalized equation. Q is equal to integral S d dot ds. So therefore charge Q can be written for the sides, for the top and for the bottom. So sides means we have 4 sides. So for the 4 sides, I have represented as a single term. So I have just written integral sides. So but sides is equal to 4 sides. D dot ds plus integral top portion d dot ds plus integral bottom portion d dot ds. That is the charge at the sides, the charge at the top and the charge at the bottom. So we know that for the sides, since it is present in the xy direction, for the sides d dot ds will be equal to 0. The understanding is your electric flux density has no component in the xy plane, because your electric flux density as per your diagram, it is present in the z axis. We can see this, your D will be here. Your electric flux density is pointing towards here. Your electric field intensity is pointing towards this side. As I said, your electric flux density and the electric field intensity are perpendicular to each other. So your electric flux density is pointing towards positive z axis and negative z axis. Therefore, we know that assumption itself we have taken, the electric fields are present in the, the infinite sheet of charge is present in the xy plane and it is nowhere related with the z axis. Therefore, for the sides, d dot ds will be equal to 0. That is, d has no component in the xy direction. And for the top surface, we know that top surface means it is in the positive z axis, bottom surface means it is in the negative z axis. So I can write d vector will be equal to, with respect to z axis I have written, therefore dz into unit vector az. Now we have to find what is this dz and what is this az. So we cannot write it as dz and az. So we have to write in terms of differential surface area. So we can write in the place of dz and az, we can write ds into capital DS, d suffix s into differential surface ds. So ds we know it is dx dy into az. Just now we have seen. Therefore, d dot ds will be equal to, in the place of d, Therefore, d dot ds will be equal to, d is nothing but for the top portion, for the top surface we are finding. So, d is with respect to your z axis, positive z axis. So, in the place of d, I have represented as dz into az. It's just, this is what I want to find, d dot ds. But what is my d? D is in the top surface, I'm assuming. So for the top surface, it is with respect to the positive z axis. Therefore, in the place of d, I have replaced with dz into az. In the place of ds, I have replaced with, in the place of ds, I have replaced with dx dy into az. So dx dy into az. We know that the dot product of same vector will be equal to 1. Therefore, d dot ds will be equal to dz into dx dot dy. Similarly, for the bottom surface, we have to find. We know that d is equal to dz and the unit vector in the negative z axis. So since it is in the negative z axis, I have represented the unit vector along the z axis a negative sign. And we know that the differential surface area will be equal to dx dy into unit vector. Since it is in the negative z axis, I have represented with the negative unit vector along the z direction. Okay. Now, d dot ds, as we have did in the top surface, the same procedure. D dot ds will be equal to, instead of d, I have to replace dz minus az. Instead of ds, I have to replace dx dy into minus az. So this minus and this minus will become positive. Again, dot product of same vector will be equal to 1. Therefore, d dot ds will be equal to dz dx dy. So in the above equation, we have to find the charge for the sides, for the top surface, for the bottom surface. We know for the sides it is equal to 0 because d has no component in the xy direction. Understanding this, d is present in the z axis. So when we talk about the sides in the figure, see in the figure, if we talk, we have assumed the rectangular, the infinite sheet is placed in the xy plane, and we have assumed a rectangular box, and the rectangular sheet is cutting the rectangular box. So since we have assumed the infinite sheet in the xy plane, the sheet which is cutting the rectangular box also lies in the xy plane. So when we talk about d, that is your electric flux density, it is independent of xy plane. Your d is present in the z axis. That's why for the sides, these are the sides. So these are the sides. All these four sides lie in the xy plane. Since d is independent of xy plane, therefore for the sides, d component is equal to 0. Okay. So coming to this equation, we have found for the sides it is equal to 0. For the top, we have found an equation, and for the bottom, we have found the equation. Just substituting for the top and the bottom in this equation 4, we get for the top surface it is integral dz dx dy, and for the bottom surface it is integral dz dx dy. Therefore, taking the dz common, we can write, taking the dz outside, it's a constant term, so taking it outside, we get integral dx dy plus d into integral dx dy. So integral dx dy plus integral dx dy will be the area of the surface because it covers the top and the bottom. Therefore, we can conclude it is the area of the surface. So instead of integral dx plus dy plus dx plus dy, we can have the parameter area, so which is represented by the letter capital A. So here one dz is there, here one dz is there. So it is twice dz. So your charge q will be equal to twice dz of A. So, but we know that charge q is equal to rho s dot A. So where rho s is the surface charge density. But we have the equation, but we have derived the equation q is equal to twice dz into A. And this is also an equation. Now only I am introducing this equation. This is also correct, where charge q is equal to the surface charge density into area of the surface. This is a new equation I am introducing now. It is standard equation. So from these two equations, I can conclude my rho s is nothing but twice that of your dz. Therefore, just cross multiplying, I can get dz is equal to rho s by 2. Okay. So therefore, d is equal to, so far we have found what is dz only. So therefore, dz means it is the electric flux density with respect to the z direction. But I have to find a generalized term, what is my electric flux density. So my electric flux density will be equal to electric flux density along the z axis and the unit vector along the z axis. Therefore, since I have found what is my dz, I can substitute in this equation. Therefore, d is equal to rho s divided by 2 into az unit vector. And again, we know the relationship. We have studied the relationship in the last class. Your electric flux density will be equal to the electric field intensity when it is multiplied epsilon naught times. So from this equation, D is equal to epsilon naught into E, I can rearrange and get E is equal to D by epsilon naught. So I have what is my D. So from this equation, I can write what is my electric field intensity. So my electric field intensity will be equal to D divided by epsilon naught. So it will become rho s divided by 2 epsilon naught into unit vector along the z direction. So I have found what is my electric flux density and what is my electric field intensity. So these results are same as obtained by the Coulomb's law for the infinite sheet of charge. Before Gauss law, we were seeing about Coulomb's law. So in the Coulomb's law for the infinite sheet of charge, we have got the same equation for the electric field. Okay. So both the results are almost the same. So what we have learned so far, the summary I'll just tell, we have learned what is Gauss law. So Gauss law is nothing but electric flux is equal to total enclosed surface. So psi is equal to Q enclosed. Now what is Q? So Q can be written as integral with respect to surface area d dot ds will be equal to volume integral V rho V dot dV. So when we apply the divergence theorem, we have concluded rho V is equal to del dot D. And then there are 4 applications for Gauss law. So with implementing the Gaussian surface, we are going to find what is our electric field intensity and what is the electric flux density. So for applying a Gaussian surface for an infinite sheet of charge, we have derived what is our electric flux density and what is our electric field intensity. And this equation, electric field intensity equation, is same as that of the equation we got in the Coulomb's law for the infinite sheet of charge. Okay. So next topic is, next application of Gauss law is uniformly charged sphere. So if we want to derive for uniformly charged sphere, we should keep it in mind what is the differential surface equation for a sphere. In under coordinate systems, we have learned 3 things. One is rectangular coordinate, cylindrical coordinate, and then the spherical coordinate. So definitely you should know the equations which we have got for the spherical coordinate system. Then only we can do this derivation. I mean, for the application of Gauss law for a uniform charged sphere. Okay. So we should know to carry over this equation. Definitely we should know the spherical coordinate system. In this application, what we are doing is, here we have taken a sphere, that is the inside sphere. Please follow my cursor. So this is my sphere, inner sphere, and I have taken an outer sphere. My outer sphere is regarded as the Gaussian surface. Okay, so this is the center for both the spheres. Okay, now the radius for the inner sphere from the center is represented as small a. The radius for the outer sphere from the center is represented as small r. I'll repeat, the radius of the inner sphere from the center to the circumference of the sphere is represented by small a. The radius of the outer sphere is represented by small r. Now, in the Gaussian surface, I have represented the second sphere only as Gaussian surface. So, in the Gaussian surface, I am going to assume a point P, and I am also going to assume, along the point P, I want to find the electric flux density. So, when my direction of electric flux density is this side, means automatically my electric field intensity will be perpendicular to the electric flux density. Okay. So simple. I have assumed two spheres. The radius of the inner sphere is small a, the radius of the outer sphere is small r, and I have fixed a point P in the Gaussian surface. This is my Gaussian surface. Outer sphere is my Gaussian surface. I have fixed a point P in the Gaussian surface, and I have also assumed along the point P my electric flux density is present. These are the assumptions we have taken. Now, how I'm going to proceed the derivation is I have to find what is my electric flux density and the electric field intensity when my radius r is less than a and when my radius r is greater than a. Okay, that is uh, that is what the two cases I have to find. Okay, otherwise I can say whether I'm going to fix the point P in the inner circle or I'm going to fix the point P in the outer circle. In simple words, I can say that whether the point P is fixed in the inner circle or the point P is fixed in the outer circle. So depends upon that. I'm going to find what is my electric field intensity equation and the um, electric flux density equation. Okay, so consider a sphere of radius a with a uniform charge density rho v. So uniform charge density, uniform volume charge density rho v, its unit is coulomb per meter square. Now let us find my electric field intensity at a point P located at a radial distance r from the center of the sphere such that r is lesser than a and r is greater than a using Gauss law. Okay. Now, first the case step. The point P is outside the sphere. Point P is outside the sphere is, this is the inner sphere. First case is I'm fixing the point P in the outer, in the Gaussian surface I'm fixing. That means this inner sphere radius is A, and therefore I can say R is greater than A. Okay. So point P is outside the sphere. The condition is R is greater than A. So the Gaussian surface passing through the point P is a spherical surface of radius R. So flux lines and the electric flux density are directed radially outwards along AR direction. So when the radius is R for the outer sphere means the unit vector along the R is AR, represented by AR. Now, differential surface area ds is considered at the point P, which is normal to the AR direction. Okay, so this is my point P. So the differential surface area for this point P is represented as ds, and it is normal to the unit vector along the R direction. Okay, in such a way I have chosen. Now, just recapping, what is this? What is the differential surface area for the sphere and the spherical coordinates we have seen? The differential surface area ds will be equal to ds with respect to r. So for the sphere, what are the three parameters? We have r, theta, and pi. So whenever we are writing a differential surface area means we have to write differential surface area with respect to r. Otherwise, we can write with respect to theta. Otherwise, we can write with respect to pi. So I have assumed that the electric flux density, otherwise the surface area at the point P ds is normal to the unit vector AR. Therefore, I have to write ds with respect to r. That is dsr I have to write. Okay. So if I want to write dsr means the other two terms which comes is theta and d pi along with the AR unit vector it will come. So this equation directly I've written over here. How I got this equation is, this equation, just check it, your spherical coordinate systems differential area with respect, differential surface with respect to the r parameter with respect to the radius. Therefore ds will be equal to r square sine theta d theta d pi. Actually what is this equation is ds suffix r, that is with normal to the AR unit vector. Therefore, ds suffix r will be equal to d theta d pi into AR unit vector. That is the basic formula. I'll repeat, ds suffix r will be equal to d theta d pi into AR unit vector. What is d theta? What is d pi? So d theta is nothing but r d theta, and d pi is nothing but r sine theta d pi. Okay, So therefore we get r square sine theta d theta d pi. So how this equation comes? Just have a look at the spherical coordinates differential surface area with respect to radius r, dsr. If you see, from there only I have referred this equation. Now, the basic equation, the total charge enclosed can be determined as, this is the Gauss law equation. Enclosed charge will be equal to volume integral rho v dot dv. So, in the place of, this is one equation I have taken. So, what is dv for the sphere? That is differential volume charge. So, dv will be equal to dr, d theta and d pi. All the three parameters will come because it is volume, no? So radius, theta and pi, all the parameters will come. So again, what is dv? Just check your spherical coordinate systems. What is dv? So from there I have referred this equation. dv will be equal to r square sine theta dr d theta d pi. This equation I have referred from the spherical coordinate systems. What is the differential volume? From there, I have directly written over here. How do we get that equation? This equation in that spherical coordinates we have derived. Now this equation is Q enclosed will be equal to volume integral rho v into dv. In the place of dv, I have replaced with r square sine theta dr d theta d pi. This rho v I have retained as same. We know what is the range for r. As we have assumed, the point P is fixed in the outer circle, that is r is greater than a. Therefore, the limit is r is equal to 0 to a, and theta lies between 0 to pi and pi lies between 0 to 2 pi. So in this equation, only rho v is a constant term. It is the volume charge density. So this rho v alone, we can take it outside. The other terms with respect to r, theta and pi, we can integrate it. So integration of rho v alone, I have taken it as outside because it is a constant. So integration of r square dr will be equal to r cube by 3. Integration of sin theta d theta will be equal to minus cos theta. Integration of d pi will be equal to pi. And accordingly, I have substituted the limits. For r, it is 0 to a. For theta, it is 0 to pi. And for pi, it is 0 to 2 pi. Okay. So substituting the limits we get, substituting all the limits and simplifying we get, it is rho v a cube. Instead of r, I have replaced with a. So a cube by 3. Instead of for t, I have replaced with pi and 0. Therefore, minus cos pi minus of minus cos 0 into 2 pi. We know that cos pi is equal to, cos 180 degree is equal to minus 1 and cos 0 is equal to 1. So here it will be cos pi is equal to minus 1. Already here one minus is there, and therefore it will be 1. And this minus and this minus will become plus, and therefore this will become cos 0 is 1. Therefore 1 plus 1 will become 2. Therefore it will become 4 pi. 2 into 2 pi. So therefore 4 pi. The rest of the term is rho v a cube divided by 3 into 4 pi. Therefore, your enclosed charge Q enclosed will be equal to 4 pi rho v a cube divided by 3. What is the unit of charge? It is coulomb. Okay. So now we have found the enclosed charge with respect to volume. What equation we have referred? Volume, differential volume we have taken as reference. Okay. The same another equation is there. Charge Q is equal to psi, that is electric flux is equal to charge, which is equal to surface integral, enclosed surface integral d dot ds. Earlier we have done with the volume. We know that Q is equal to integral S d dot ds, which is equal to integral V rho V dot dV. So first derivation we have done for volume rho V dot dV. The second one, the same Gauss law, we also have d dot ds equation. So this ds equation, in the place of d, I have replaced with, I have used the term dr just to differentiate the terms. D is nothing but d only. Since it is with respect to the radius r, I have represented as dr. And this ds, where did I refer is, ds is the differential surface with respect to r, which I have referred from the spherical coordinate system. So ds is equal to r square sine theta. Actually, ds is equal to d theta d pi into ar unit vector. Okay, d theta is nothing but r d theta, and d pi will be equal to r sine theta d pi. So when we are substituting, we get ds is equal to r square sine theta d pi. So in this, dr is a constant term. It is electric flux density with respect to the r radius r. Therefore, we have to integrate with respect to theta and the pi. So dr is treated as a constant term. So taking the constant term outside, I have differentiated, I have integrated with respect to theta and with respect to pi. So r square is also a constant. So once I integrate it, I have got the equation q is equal to 4 pi r square into dr. So cross multiplying, I'll get dr is equal to q divided by 4 pi r square. And therefore d is equal to nothing but dr into ar unit vector. I'll repeat, I have found only dr. So d is nothing but dr into ar unit vector. So I know what is dr. So dr I've written dot ar unit vector. Okay, and I know the equation E is equal to d by epsilon naught. Okay, so I know what is d, and therefore d by epsilon naught. Therefore, the electric field intensity E will be equal to q divided by 4 pi epsilon naught r square into ar. Its unit is volume per meter. Okay, now I found two equations. Once again, sorry, there's no charge. Okay, so now we have found. Sorry, I put my laptop in charge. Okay, now we have found two equations for charge. One is with respect to volume and the other one is with respect to d dot ds. So with respect to volume, we have found 4 pi by 3 rho v a cube, which is equal to, with respect to ds dot d dot ds, we have found that is 4 pi r square into dr. So we have found two enclosed surface, which is with respect to surface integral, one is with respect to volume integral. So the final equations what we got for surface and volume integrals, we have equated both the things. Once we have equated both the things, I'll try to find, solving all the possible terms, I'll try to find cancelling all the possible terms, I try to find what is my dr. So dr will be equal to rho v a cube divided by 3r square. Therefore, d will be equal to, I have found only dr. So d is nothing but dr into unit vector. So d will be equal to dr into unit vector along the r. So what is dr? Rho v a cube divided by 3r square into ar. So this is the electric flux density when the condition R is greater than A. Otherwise, I can say when the point P is fixed in the second sphere. Now, the second case is when the point P is inside the sphere. That is, in the first sphere, I am going to choose the point P. And through the point P, I am going to define what is my electric flux density D. So, D is equal to dr into AR. Okay. Now, this is my Gaussian surface. Earlier, I have assumed the outer surface, outer sphere as a Gaussian surface. Now, I am assuming the inner sphere as the Gaussian surface. Okay. Now, we'll try to find in the same procedure. Fine. So what is your enclosed charge? Enclosed charge with respect to volume and with respect to surface area we are going to find. So with respect to volume, the equation is rho v into dv. We know what is dv, r square sine theta dr d theta into d pi. This equation I referred from the spherical coordinates for the differential volume. Then I have integrated with respect to r, theta and pi as I did for the previous case. So I'll get this equation. Once I integrate it and substitute the limits, I get enclosed charge will be equal to 4 pi r square rho v divided by 3. Here, the only difference between the previous equation for the case 1 and case 2 is there the limits was 0 to a, here the limits was 0 to r. That is the only difference. So there we got a cube divided by 3, here we are getting r cube divided by 3. Otherwise both the equations are same. The only thing is the difference is where you fix the point and what is the radius of that sphere. That is what the only difference. Okay. And similarly, already we have found with respect to this differential surface area. So equating 2 and 3, we get 4 pi r square rho v divided by 3 into 4 equal to 4 pi r square dr. Cancelling all the possible terms, we get dr is equal to r by 3 into rho v, and d is equal to dr into unit vector along the direction r. Therefore, d is equal to dr. dr is r by 3 rho v into unit vector ar. So this is for the electric flux density is for the condition r less than or equal to a, otherwise r lies between 0 to a. So thus we can conclude the electric flux density d is equal to rho v a cube divided by 3r square ar unit vector for r greater than or equal to a, and r by 3 rho v into ar for r lying between 0 to a. Okay, hope you have understood the application of Gauss law for the uniformly distributed sphere. The third application is for a point charge. Okay, so I have taken a point charge. Point charge means it's not a continuous, just a point. Okay, so I have assumed I have chosen the point P in space. So now I have to determine what is the electric flux density along this point P. So the radius somewhere in space I have kept a point P. I have to define what is my electric flux density D along the direction point P. Okay, through passing through the point P, not along the direction, passing through the point P. I have assumed the radius as R. Okay, now so we know that Q is equal to D dot ds. So in the place of D, I have replaced with dr. dr in sense the flux density with respect to the radius r. Why with respect to radius r means because I have taken a point P over here, and from the center and to the point P I have assumed the radius r. That's why I have put a suffix r over here, dr. A spherical surface centered at the origin is the Gaussian surface. So the sphere is the Gaussian surface. Therefore, Q is equal to, since this dr term is a constant term, I have taken as outside. Therefore, enclosed surface integral ds. So enclosed surface integral ds will be equal to nothing but the surface area of the Gaussian surface. So area of the sphere is nothing but 4 pi r square. So instead of integral ds, I can replace with 4 pi r square. Therefore, I can write this equation q is equal to dr into, in the place of integral ds, I'll replace with the surface area of the Gaussian surface. Therefore, dr into 4 pi r square. Since d is equal to dr into unit vector, as here I can write d is equal to q divided by 4 pi r square into ar, because I have written here q in the place of d. I have but d is equal to dr into unit vector. So I want to find what is my d. So cross multiplying, I'll get q divided by 4 pi r square into unit vector along the direction r. Fourth application is for an infinite line charge. Okay, now this is an infinite line I have taken. This is the infinite line I have taken. So this infinite line, follow my cursor. So this is my infinite line. I mean, just remove all your, remove from your eyesight the cylindrical surface and all. Just follow my words in the cursor. So this is the line, infinite line I have taken. Otherwise, finite line I have taken for practical purpose. I have taken a finite line. So this finite line is having a line charge rho L, line charge density rho L, which is having a unit coulomb per meter. Now I have assumed a Gaussian surface surrounding this line charge. I am assuming a cylindrical Gaussian surface. So this cylinder is my Gaussian surface. So the cylinder Gaussian surface, this length is L, and I am fixing a point P in the circumference of the cylinder. So passing through the point P, I have to find what is my electric flux density. So Gauss-Lia fully, my intention is to find what is my electric flux density. So suppose the infinite line of uniform charge rho L, which is having the unit coulomb per meter, lies along the z axis. As you see the diagram itself, you can understand my infinite line is lying along the z axis. So to find the electric flux density D at a point P, choose a cylindrical surface to satisfy the symmetry condition. Why we are choosing a cylindrical surface is to satisfy the symmetrical condition. So we know the basic formula, charge Q is equal to surface integral D dot ds. Since it is a line integral, since we have assumed a line charge density, since we have assumed the line charge density, my charge for a line charge density will be equal to rho L into L. Okay. So therefore, there are two equations over here. The general expression for Gauss law is Q is equal to surface integral D dot ds. But here in the application, I have taken for an infinite line. Therefore, the charge Q for an infinite line will be equal to rho L into D, rho L into L. Okay. So now D can be written as D rho into A rho. Why D rho into A rho? Why the suffix rho comes? How come D is changed to D rho? Means this is basic formula. D will be equal to how we have written in the previous case. D is equal to dr into AR unit vector. Similarly, I have written D is equal to D rho into A rho unit vector. But why it is rho means for the infinite line charge, my charge density is rho. So that's why I put a suffix rho. So d rho into unit vector along the rho direction. Therefore, Q will be equal to, in the place of D, I have replaced with d rho A rho. So I have written integral d rho ds. Okay. So d rho is a constant term. Therefore, integral is with respect to only surface. So we know that surface area of a Gaussian surface, again it is a cylinder. So since it is a cylinder, the surface integral ds will be equal to 2 pi rho L. Okay. From where I got this equation is, if you check your cylindrical surface differential surface area, from there I have referred this. For a cylindrical coordinate system, for differential surface with respect to rho, if you check it out, from there I have referred this equation. So integral is ds for a cylindrical surface, Gaussian surface will be equal to 2 pi rho L. Therefore, in this place, in the place of integral ds, I have replaced with 2 pi rho s. Therefore, Q is equal to d rho 2 pi rho L. Therefore, D is equal to, we know D is equal to d rho into, actually ds is equal to Q divided by 2 pi rho L. Here there is a mistake, it is ds. Okay. Similarly, when I replace this Q with the line charge equation, earlier itself I said, since it is a line charge, Q can also be represented as rho L into L. Therefore, I have written, instead of Q, I have written rho L divided by 2 pi rho L. Okay, actually this is d rho. It is not d, it is d rho. Here also it is d rho. So this L and L will get cancelled, and therefore I can write D is equal to d rho into A rho unit vector. Therefore, D is equal to rho L divided by 2 pi rho into unit vector along the direction rho. So this finishes your Gauss law application. So for Gauss law, what is Gauss law? We have seen, and there are 4 applications for the Gauss law: for an infinite sheet of charge, for an infinite line charge, then for a uniformly distributed sphere, and then for the point charge. So for all the 4 applications of Gauss law, we have derived what is our electric flux density capital D and what is the electric field intensity capital E. So hope you have understood what is Gauss law and its applications. So in the next class, we'll see the next topic, electric potential.